everyone. Thank you for joining me today. My name is Hana Salati. I'm a research fellow at RMIT University. In this presentation, I'm going to talk about a fan respirator reduces CO2 concentrations and refreshes air temperature for inhalation. Although over 3 years have passed since the start of COVID-19 pandemic, masks and respirators are still mandatory in some indoor settings, such as public transport and hospitals. The N95 respirator is a respiratory personal protective equipment that protects against infection respiratory disease, including COVID-19. N95 respirators are made of 4 layers, which causes resistance to inhalation and exhalation airflow. It is expected to affect nasal airflow, where accumulated exhaled carbon dioxide concentration in the mask region is reinhaled. It increases respiratory rate, brain blood flow, metabolic stress, headache, dizziness, confusion, and dyspnea. In the first part of our study, we investigated the nasal airflow dynamics during respiration with and without an N95 respirator, driven by airflow through the nasal cavity to assess the effect of the respirator on breathing conditions during respiration. We found that at the end of exhalation, CO2 concentration reached 28,000 ppm, where often instead of inhaling fresh air containing a low CO2 concentration. So the accumulated CO2 in the mask is inhaled. Therefore, a respirator could cause excessive CO2 inhalation by approximately 7 times greater per breath compared with normal breathing. This finding has been validated through an experimental measurement, as is shown in this graph, which shows 7 times CO2 inhalation level during respirator breathing. So, fan-powered masks have been proposed to resolve respiratory-related complications and provide breathing comfort for an extended period. In the second part of the study, we aim to understand the breathing airflow characteristics inside an N95 respirator with different fan locations, top, side, and bottom, and compare their inhalation air quality from different fan locations with N95 respirator breathing and normal breathing. The nasal vestibules from a healthy human subjects were taken from a CT scan and imported to 3D slicer segmentation software. An axial microfan were represented with a cylindrical and a diameter of 20 mm on the respirator, as it is shown in this figure, in 3 different locations: top, bottom, and side. The respiratory cycle was simplified to pure sine waves based on measured physiology data. And an N95 mask surface was set as a porous zone, and we consider the flow rate of the fan as a 0.8 CFM. A fan boundary condition was used in the simulation. At time 3.6 seconds, the high temperature filled the entire top fan position compared to the other location side. For the bottom fan, the high temperature air accumulated only around the bottom of the mask. During inhalation, the high temperature air inside the respirator was inhaled back into the nasal cavity. The temperature in the respirator decreased for different locations. Here is the CO2 concentration, the contour of the CO2 concentration for different side locations. The fan's location at the bottom of the respirator is parallel to the nostril jet, which reduce the flow circulation inside the respirator. During inhalation, the residual CO2 inside the respirator during exhalation was discharged from the bottom fan respirator. Therefore, the fresh air containing a low level of CO2, around 385 ppm, which entered the mask region, and high CO2 concentration built up is avoided during inhalation, which is shown in this figure. An animation of CO2 concentration in the mid-right nasal passage at different fan locations, including top, side, bottom, is shown here. This graph shows CO2 concentration, water vapor mass fraction, and air temperature variation during the first and second breathing cycles. The results of the fan power respirator with different fan locations are compared with the no fan respirator. Breathing without a fan respirator increased all parameters like an increase in the moisture and CO2 content and temperature. A slight increase in the CO2 level occurred in the second breathing cycle, which demonstrates the residual buildup of the gas mixture from exhalation. And the bottom fan position also produced the greatest temperature decrease to 20 degrees. This figure shows time average inhaled CO2 concentration rate during the first and second inhalation cycles of breathing in a respirator mask with the 3 positions fan and without a fan. The bottom fan respirator produced the greatest decrease in the average CO2 concentration, 87% compared with the no fan respirator breathing. The performance of the top and side fan positions also reduced the average CO2 concentration, but not as well as the bottom fan position, where the reduction ranged from 67 to 78%. Thank you all for your attention during this presentation. To summarize, our research has highlighted the following key takeaways. A respirator could cause excessive CO2 inhalation by approximately 7 times greater per breath compared with normal breathing. The inhaled air was sufficiently refreshed when a bottom fan position was used, where the air temperature in the mask for inhalation returned to the ambient temperature, eliminating the nasal stuffiness sensation associated with fanless respirator. The nostril jet during exhalation moved towards the bottom of mask. Therefore, the top fan and side fan couldn't discharge the exhaled gas quickly. The use of fan has been demonstrated as a viable method for ventilation the air within a respirator. I hope that our findings have provided valuable insights and sparked further discussion on this topic. Thank you once again for your time and attention.